So today we're gonna start talking about parameter estimation. Sometimes it's called point estimation of parameters or something like that. We're gonna be covering a couple of sections in chapters 7, 8, and 10 of the book. So you're gonna have to do a little jumping around back and forth between different sections, but for the most part, our topics are gonna talk about parameter estimates. Ubong, that's fine. I think what I can do in the chat, Ubong is asking about the group and the upcoming test. You know what I'll do, because I also want to cover the material. Let me cover the material for the class today, and at the end of the class, I'm going to repeat the test announcements. That way, anyone that missed them can hear them, and anybody that already heard them can, can leave. So just give me a quick reminder at the end of the class, maybe the last 5 minutes I can dedicate to going over the test announcements. Anyway, today we're going to talk about parameter estimation. I think it's an interesting rehash of some of the stuff we've already covered. And whereas in previous sections, when we've learned about different parameters and measures and metrics, we kind of worked with individual random variables, or maybe even with joint random variables, but we've always worked with the experiment, let's say with one experiment happening at a time. Now, when we talk about parameter estimations, we're going to start to deal with multiple experiments happening, multiple experiments of the same type occurring. And that's going to make our work a little bit more consolidated, and we'll see how in just a second. So let's start with some definitions. I think it's important to maybe define a few terms that we're going to be using throughout the rest of the class. So the first thing I'd like to talk about is called a point estimate. And a point estimate is essentially, I would say, a good for a random variable. You can actually come up with your own point estimates for different multiple experiments without actually running the experiment themselves, right? So you can think of any experiment where you can more or less come up with a reasonable value, right, for the experiment. For example, I can say something like, if you've driven down 400, let's say you want to start a study to determine the median velocity of drivers on 400. Do you think you can give me a point estimate for that value? We're trying to start a study. We'd like to determine the median velocity of drivers. Of course, for the study, you have to actually go in and find a way to calculate the velocities of all the cars. But do you think there's a way to get a reasonable guess, right, for that value? The median velocity of drivers on Highway 400. Georgia 400, it's a state road. Any ideas? I mean, you can think of any other state road. Let's just do a bigger one. Let's say I-75, which is close to our campus. Okay, we see about 70 miles an hour. I think that's a reasonable estimate. I would say that without running any guesses, I could just base it on the speed limit, says a student in the chat, a bit higher. Yeah, I think those are good ways to determine or to guess a value. You may think, well, the speed limit certainly is going to play a factor in here, right? Because if there was no speed limit, it'd be a little bit harder to guess. We'd have to think of things like lane size. We'd have to think of how busy the road is. But for the most part, all those things are kind of accounted for in the speed limit, right? So if you look at the speed limit, you may think perhaps the median driver drives a little bit higher than the speed limit. And I think those are all good good ways to come up with a guess. And that's the point of point estimates, right? You want to come up with a good guess that's reasonable. It doesn't have to be exact. It may not be exact. In fact, in most cases, it will not be exact. But it should be reasonable, so to a certain degree. Now, at this point, this sounds a little bit abstract for me to say, well, what's the degree of reasonableness, right? But we're going to talk a little bit in the next class about confidence in our estimates. But so for now, let's just say it's something that it's reasonable. So if I say that the median speed in in the leftmost lane in I-75 is 20 miles an hour, you may say that's not really a reasonable guess, right? Because the left lane is the passing lane. I know most people in Georgia don't know this, but the left lane is a passing lane, right? And in those highways. So you know that for sure the speed limit will be higher than the average median speed will be higher than the speed limits. There's a question in the chat. Would the wisdom of crowds be a point estimate? Yeah, I would say good. It would be a good one, and that's kind of where the whole idea of wisdom of crowds comes into play, right? If you want a point estimate, you could actually just ask a bunch of people and then get their insights. I would say with something like a speed limit, with a medium velocity, it's even better to use wisdom of crowds, just because the crowds themselves may have, or the people in the crowd, the members of the crowd themselves may actually have experience driving on that road. So they may look at their own, right, their own experience in order to come up with a reasonable estimate. If I drive right at the speed limit and everybody's always passing me, I'm gonna guess that the median driver drives a little bit higher than the speed limit, right? So those are good, very, very good methods, right, for obtaining a point estimate. Now, the point of this class is not to say that you're gonna be guessing things from now on, but the idea is we need to at least come up with a value that's reasonable for a random variable. Now, I can't really tell you what is a reasonable value. It's actually a lot easier to say what are not reasonable values. Like I said, for the highway, I'm not really sure what a reasonable value would be, but perhaps a non-reasonable value would be 20 miles an hour if the speed limit is 70, right? Perhaps a non-reasonable value would be 120 miles an hour, because a lot of people, even though their cars can get that far, they don't really, push it that high up, right? Or they did, they would just crash. So I think there are ways to obtain not reasonable values, right? Unreasonable values, and you can use those to kind of fix in on a reasonable value. So those are, I would say that's a strategy you might want to think of. If you can't really come up with a good guess, think of very, very bad guesses, and then just kind of work your way in as a process of elimination, right, to get your good guess. Now, the reasoning behind a point estimate, right, is that even though you're going to have variability between your different measurements and your different observations, there is an expected range, right? And the point estimate has to be so far within that expected range that you can almost guarantee that it's not going to fall out of the expected range. All right? Typically, the statistician is the one who selects the point estimate. And of course, you need to understand that the point estimate will vary depending on the properties of the experiments themselves. So you can think of all the different, let's say, all the different possible speeds that a Honda Civic can actually attain. Let's say just straight out of the dealer, no modifications. If you think of all the speeds that it can attain, you know that at least those are within the reasonable values, because it cannot go higher and it cannot go lower than 0. And then you can start adding things, adding other factors such as, well, what's the speed limit of the road? We know that if you are driving more than 15 miles over the speed limit, that's considered reckless driving. I know by experience. So at that point, it's less reasonable to see people, or at least the median driver, driving at those speeds. But you also know that if you drive less than 20 miles under the speed limit, I guess more than 20 miles under the speed limit, then that's considered careless driving. And in that case, also, you may understand that it's less reasonable to find people in that range. We're not really here to discuss transportation, even though that's actually a little bit relevant to your field. But the whole point is that you can come up with a point estimate, but the better you understand the experiment, the better your point estimate will be, which is why it's important to understand your experiment before you actually try to analyze it. Now, we've already learned about all the different measures of a random variable. We talked about mean, variance, standard deviation, et cetera, et cetera, et cetera. Now, what I would like to do now, moving forward, is to divide those measures into 2 different groups. So all the different measures of random experiments, we are going to divide them into parameters. and statistics, roll credits, right? So the difference between parameters and statistics is that parameters are going to depend on one or more random variables, but statistics are going to depend on random variables that are functions of other random variables. It's a bit of a mouthful there, so I'll explain it in just a second. So for now, let's look at what we are classifying as a parameter and what we are classifying as a statistic. Our mean, variance, and standard deviation are going to be considered parameters. So mean, variance, and standard deviation. If it's easier, you can use their signs, so mu, sigma squared, and sigma. Those are all considered parameters. Additional parameters include the covariance and the correlation. Now you notice that these parameters essentially depend on the probability distribution of one or more random variables. Now a statistic would include all those numerical measures that we talked about in the previous week. So things like the sample mean, sample variance, sample standard deviation, sample median, and sample mode, or I'll just call them median and mode. Those are all statistics. Okay. Each of these measures, whether parameters or statistics, can serve as a point estimate for a particular property or particular part of an experiment. How you select the measure depends on not just the experiment itself, but also your goals for that experiment. So we've already done this example before, but let's rehash this example so that we can now express it in terms of parameters and statistics. Let's say that you are a realtor. You are advertising a sale in the neighborhood. I know we've already done this before, all right, but you're the realtor. You want to advertise a sale. You want to give the impression that the neighborhood is upscale. Now, if somebody asks you a ballpark estimate of the cost of a house in the neighborhood, like let's say you're a realtor, you're working with a homeowner in one of those houses, but you don't really know what the other homeowners, are going to sell their houses for. So if somebody asks you a ballpark estimate, which point estimate do you think, which of these measures would you select for your point estimate? So somebody says, give me a ballpark. What do you think a house would sell for? And you're a realtor and you are hoping to give the impression of an upscale house. Okay, so I see some examples in the chat, and that's good. But here, I'm not really asking for a number, right? A specific number. I'm saying within this list of things, right? Okay, that's a little bit better, right? So I see in the chat that sample mean if it's a more upscale neighborhood. And that's true, because if you are in a more upscale neighborhood, you will definitely going to have outliers on the higher end. And those outliers are going to push your sample mean a little bit higher. The whole point is in saying this is a reasonable guess. I'm not really lying. I am using data, right? Maybe not all the data, but I am using a point estimate for this neighborhood. And of course, if you are a homeowner and you are actually moving to a new neighborhood, you want to guess on how much your new house will cost in order to finance it, right? You know that you would probably use the sample median as your point estimate, because the sample median, it doesn't really give you the average cost of a house, but it does give you the cost of an average house. And that's typically what you would want to use if you want to have a good estimate of what you, right, will be spending on a house. I'm not saying that you are all average. Maybe some of you are extraordinary. Who knows? If you surprise me, then good. But the whole idea is, if you want to know a little bit about how the price will look like for what the price will look like for you, you don't really want to look at the average house price. You want to look at the price of an average house. The placement of the word average there is crucial, right? There's a difference between the average house price and the price of an average house. Just like there's a difference between average salary of a person in a company versus the salary of an average worker in a company. So, of course, you want to choose the parameter that works best for you, depending on what it is you're trying to seek from your experiment. Now, let's talk a little bit about how we do this parameter estimation. So let's recall that you can create random variables that are functions of other variables. We didn't really go into too much detail, but we did say that if you have a variable, you can create a function of that variable, and that function, it's in itself a different random variable. One example is when we are calculating the covariance. You may remember, and I'm just going to recall here. Okay, just saw a message in the chat, and a student is going to restart the computer. That's fine. So for the covariance, right, you may recall that there was a function that was the mean of xy. In that case, how did we find the mean of xy? Well, we had our variable x, and we had our variable y, and we have different points for each. So to find the variable called xy, all we have to do is multiply x times y. That's all we did, right? And then that itself is a random variable. X times y, it's in itself a random variable, so that we can find the mean of that random variable. If we wanted to, we could find other parameters of that random variable as well. So what I'm trying to get at here is that a function of one or more random variables, it's by itself a random variable as well. So your random variable can be, let's say, x. But if you decide to create a table with all of your x values squared, that x squared, it's by itself another random variable with its own mean, variance, standard deviation, etc. So I'm saying this because if we know that we can create random variables by making functions of other random variables, then we can actually conclude the following, right? All statistics are functions of random variables. Think of it this way: you have the mean. And what was the mean? The mean was the sum of all of the values in your random variable divided by the number of outcomes in that random variable. So it's a function of the random variable, right? Same thing occurs with the sample variance, sample standard deviation, median, etc. They're all functions of other variables. So if all statistics are functions of random variables, and you know that the functions of random variables are also random variables, then that means that all statistics are, by themselves, also random variables. So the key thing here is to know that these statistics are themselves random variables. And the reason statistics are random variables is because they are functions of other random variables. And a function of other random variable, it's a random variable itself. So what does that mean? If a statistic is a random variable, that means that that statistic, that random variable, should have its own statistics themselves. So you can calculate or you can determine the statistics of the statistics because they are themselves random variables. Now, we're not going to go very esoteric here. We're not going to try to calculate an infinite number of statistics, etc., etc. But what we do want to understand is that these statistics for different experiments can be viewed themselves as random variables, right, with their own probability distribution. And the probability distribution of a statistic is called a sampling distribution. So all statistics are random variables themselves with their own probability distributions. And those probability distributions are going to be called sampling distributions. There are four main types of sampling distributions that we are going to study in this class. The first one, which would be the expected one, is a normal distribution. We know that a lot of physical processes, if not most, follow a normal distribution. And as a lot of sampling distributions of experiments of physical properties will also follow a standard normal distribution. One interesting thing is that a lot of different statistics, even though the statistics random variables will not follow a normal distribution, the sampling distribution of those statistics could follow normal distributions. It sounds a little bit crazy, but we will find that a lot of these actually work in this way. So the four types of sampling distributions we're going to study in this class are going to be the following. We'll be dealing with normal distributions, actually standard normal distributions, which we've already dealt with before, but we're going to revisit. And three others that we haven't really covered. We're going to be dealing with the student's t distribution, we're going to be dealing with the chi, he, chi, chai, whatever you want to call it, square distribution. And we are going to be dealing with the F distribution. You know that the standard normal random variable carries a value of z. The student's t distribution will carry a variable t. The he squared distribution carries, well, he squared, and the F distribution carries a variable f, just to make our writing a little bit simpler. It's really interesting because these distributions are actually related to different statistics. So for example, the z and the t distributions, so the standard normal and the student's t distributions, are related to the sampling distribution of means. In other words, the probability distribution of the sample mean of a random variable. Whereas the chi-squared distribution and the F distribution are related to the sampling distribution of variances. So if you thought you were free from all the probability distributions that we kind of stopped talking about 2 weeks ago, then we're going to go back into these probability distributions, except that now, instead of seeing them as probability distributions of one random variable, we're going to be seeing them as probability distributions of samples, of statistics, which themselves depend on random variables. In order to talk a little bit about how the standard normal distribution relates to the different sampling distributions, I think we are going to have to revisit the central limit theorem. You may recall that I started talking about the central limit theorem back when we introduced the normal distribution, but we mentioned that we were only going to cover it just a little bit, and then we're going to go into a little bit more detail, which is what I plan to do now. So in order to understand how the central theorem, right, can help us understand all these different sampling distributions, let's first make sure that we're all on the same page regarding what we are talking about here when we talk about samples and statistics and all these things. Let's consider, right, a set of random variables, okay? Different random variables, they are all independent and they all have the same probability distribution. So I can think of a random variable, I can call it x1. This can be one random variable. This can be another random variable. This can be another random variable. And we can have as many, right? Let's say all the way up to n random variables. Okay? All of these random variables are going to be independent from each other. And all of these random variables are going to have the same probability distribution. Whatever that is, doesn't matter, but they'll have the same probability distribution. So you can think of it as, for example, running an experiment, the same experiment, multiple times. And x1, x2, x3 being the random variables that contain the outcomes of each time you run the experiment. Now, if you run the experiment in exactly the same fashion every time, that means that the outcomes should all have the same probability distribution. Of course, the whole point of statistics is to study variability, which means that even though the outcomes all have the same probability distributions, that doesn't mean that the outcomes themselves will be the same, right? You can think, for example, of rolling a die. If you roll a die, x1 can be the first time you roll your die. x2 can be the second time you roll your die. x3 can be the third time, and so on. For all of these random variables, you'll have the same probability distribution, which is that every number in the die has a 1 in 6 chance of being rolled. So they all have the same probability distribution. However, your second roll will have no bearing on the fourth roll. So these rolls will all be independent of each other. You can roll one, you can roll another one. One is not going to affect the other because they are independent. Now, if that's the case, then what we have is a set of random variables, each with the same probability distribution. That doesn't mean that it's going to be the same outcome, right? You can roll a die n times, let's say 7 times. You're not going to have the same 7 outcomes. And if you do, there's actually a probability for that, but it's slow, right? It's low. So each random variable consists of the possible outcomes of a random experiment. And if you're repeating the same experiment, then your outcomes should have the same probability distribution. Now here's the thing. If all of the random variables have the same probability distribution, then they should have the same mean and the same variance. Right? Because you have all of your outcomes and a probability associated with each outcome, which means that you can calculate the mean and you can calculate the variance. And for all of your cases, for all of your random variables, you're going to have the same mean and the same variance. So what we can do now is we can take the sample mean of this group of variables. In other words, take all of these variables, right, once you run your experiment, and then take the sample mean of all of these variables after you run the experiment. Okay, so let's say you roll your die. Let's just give it a concrete number. You roll your die 7 times. For your first roll, you write down the outcome. For the second roll, you write down the number. Let's say 2, 3, 1, 4, 2, 2, whatever. You can take those outcomes, those results, and then take the sample mean of that, right? That's called the sample mean of a random sample. And what that sample mean will look like, well, it's a sample mean, so it should be simply the sum of all of your outcomes, or sorry, of each of your outcomes in each of these random variables. So let's say the sum of all of my xi, so x1, x2, x3, x4, all the way to xn, and then just divided by the number of random variables, which would be n. So it's kind of like we're repeating the procedure we learned last week, except that now instead of dealing with just measures, just observations, we're actually treating each observation as a random variable with its own probability distribution. I'll just say from I equals 1 to n. This sample mean itself, it's going to be a random variable, right? Because what you're doing now, right, is you are taking the mean of all of the random variables. So you're taking the mean of all the random variables. We already mentioned that a statistic is a function of a random variable, and a function of a random variable, it's itself a random variable. What that means is that this sample mean is going to be itself a random variable with a mean equal to mu. So we know that each of these random variables has a mean, the same mean, we'll just call it mu. And if we take these random variables and calculate the mean of those random variables, we're going to get the sample mean. And if we get all of the values in our sample mean, all the possible outcomes of a sample mean, the mean of those outcomes is also going to be mu. It's going to be the same mean. The variance of the sample mean, remember, variance is twice the dispersion. In this case, the variance would be sigma squared over n. So what we're doing here, as abstract as it sounds, is we're taking these different random variables, we're treating them as if they were just individual outcomes so that we can calculate the mean of those random variables. Now that mean itself is a random variable, which means that it's going to have its own mean and its own variance. Now the relationship between the mean and variance of the sample mean and the mean and variance of the individual random variables is the following. The mean is the same, just mu, and the variance for the sample mean is going to be the variance of the other variables divided by n, where n is the number of random variables. You can keep repeating this over and over again, but that's not really necessary, right? The important thing is that we have our random variables, and we can figure out what the mean of those random variables will be, and that mean itself will have a mean of mu and a variance of sigma squared over n. So it's like we're moving up in layers, right, in different levels. We had a level where we're dealing with each random variable individually, but now if we combine them, we can go up a level and deal with all the random variables as one sample mean. Now, here's the thing. If we have a lot of variables in a random sample, in fact, let's say we have so many random variables that n tends to infinity, then the sample mean, right, will actually follow a normal distribution. In other words, if we roll a die an infinite number of times, the sample mean will follow, the sample mean of those rolls will follow a normal distribution. And of course, we can standardize a normal distribution relatively easily. You may recall from our previous classes on the normal distribution, we can create a standard normal random variable by taking my normal random variable, subtracting the mean, and then dividing it by the standard deviation. Of course, here, My variance is sigma squared over n, which means that my standard deviation will be sigma over square root of n. So in the chat, we have a question. Will the mean of the sample mean have the same value as the sample mean? Not quite, because remember, the sample mean is not just one value, right? It's going to be multiple values. Let me try to illustrate this a little bit more concrete, but a little bit more less generic and more concrete. You have your random variables. Let's say that your first random variable, and let's call it x1, has the following probability distribution. You have a value, an outcome, and I'm just going to make up numbers here so that we're just make up easy numbers. You can have either 0, 1, or 2. The probability of 0 is 0.25, the probability of 1 is 0.50, the probability of 2 is 0.25. Okay? If you run your experiment the first time, x1 will represent the possible outcomes of your experiment with their own probabilities. Now, your outcome could be 0, could be 1, could be 2. They have different probabilities, but it could be any of these three. If you run your experiment and it's the same experiment, then you're going to have another set of outcomes. We'll call that x2. But because you're running the experiment in the same way, your probability distribution will be exactly the same. If you run the experiment a third time, again, you can have the same outcomes with the same probability distributions because you're running the experiment in the same fashion. Now, here's the thing. Just because you're running the same experiment doesn't mean that your outcomes will be exactly the same. If they were, we wouldn't need statistics, which means that x1, you could have an outcome of 1. Perhaps x2, you also have an outcome of 1, but x3, let's say that your outcome is no longer 1. Let's say your outcome is 0. So what I have now is I ran my experiment 3 times and obtained 3 different outcomes. Okay. Now what the sample mean will be is the mean of each of those outcomes. So your sample mean, for example, will consist of the mean, let's say, of the 3 outcomes if your outcomes were, let's say, 0, 0, and 0. So the mean of 0, 0, 0 is just 0. And the probability of those outcomes being 0, 0, 0 are going to be, well, 25% times 25% times 25%, right? And let me just grab my calculator to get that. About 1%. I'm going to round here just so that we can make it a little bit quicker, right? You can also get a sample mean. What if your first outcome is 0, your second outcome is 0, your third outcome is 1, right? Now, if that's the case, you have another sample mean, right? 0 plus 0 plus 1 divided by 3, that's 0.33. Now, the probability of your outcomes being of your outcomes having a sample mean of 0.33 are going to be 0.25 times 0.25 times 0.50. So it's about 3%. You could also have a sample mean if your outcomes were 0, 0, and 2, right? In that case, your mean will be 0 plus 0 plus 2 divided by 3. In that case, it's about 0.67. And the probability of that occurring is 0.25 times 0.25 times 0.25, or just roughly 1 or 2%. So you can keep repeating this, right? I'm not going to repeat it, but you can keep repeating this for, let's say, 0, 1, 0, 0, 1, 1, 0, 1, 2, 1, 0, 0, 1, 0, 1, 1, 0, 2, 0 to 0, 0 to 1, 0 to 2. You can repeat it and form a probability distribution that consists of the sample means of all of the possible answers, of all of the possible outcomes in your experiment. But that, as you can see, consists of outcome and probability. So that itself is a random variable with a probability distribution. Now that mean, mu, the mean of the sample mean is going to be the mean of all these values. You take all these values, right? You multiply them by their probabilities and you add them up. You're going to get a mean that's actually going to be equal to the mean of each of these individual variables. So you take 0 times 0.25, that's 0. 1 times 0.60, that's 0.50, that's 0.50. And then 2 times 0.25, that's another 0.50, right? That gives you a mean of 1. So all of these three, each of these three will have a mean of 1. If you take all of the answers for this sample mean, if you take all these values and calculate the mean of all these values, you should also get 1. Right? So that's the thing. The mean of the sample mean has the same mean as the means of these individual values, but the value of the sample mean depends, right? There's variability here. It could be one of multiple values. So far, does that procedure make sense? The idea of a sample mean? If it doesn't, we can just do a full experiment and go through all the calculations. But if it does make sense, we can go on to a more concrete or practical example. So what do you think? All right, looks like it does make sense. So let's keep moving on. So if instead of 3 repeats, we repeat the experiment an infinite number of times, then this variable will actually follow a normal distribution. We can plot it, it'll plot the bell curve. Now, we can standardize that normal distribution with a typical our method. We know that we can standardize a normal distribution by taking the value minus the mean divided by the standard deviation. Now here, because the standard deviation of this sample mean is actually different from the standard deviation of the individual random variables, then we just use this notation, right? The standard deviation will be the square root of this term. The square root of sigma squared is just sigma, and then the square root of n is right here. So this is how we will standardize a normal distribution of a sampling distribution. Let's go with a practical example, like I said earlier. I don't think it's necessary to actually do all the calculations. I think you can take my word for it, but if you don't, then you can also do the calculations yourself, and you'll find that these two will be met if you actually go through the procedure of calculating or getting the sample mean and then calculating its mean and its variance. So this is an example that's straight from the book, or our textbook, the one that we're using, not one of the other fun books that I'm reading. Here, we're going to be dealing with resistors and with manufacturing, right? So let's suppose that you're manufacturing resistors, and your resistors are going to have a mean resistance of 100 ohms. We'll say that the standard deviation, right, of your resistors, of the resistance of your resistors, is about 10 ohms. If the distribution of the resistance is a normal distribution, so if we were to plot resistance and probability, so resistance and probability, and we get a normal distribution, my question would be, what is the probability that a random sample, so if you take a random sample of 25 resistors, will have an average resistance less than 95 ohms. So let me just break that down. Say we take a random sample of 25 resistors from your group. And I'd like to find the probability that your random sample will have an average resistance. Okay, that's a key word, right? Average resistance. So I'll find probability that the average resistance, I'll just call it X bar, of your random sample is less than 95 ohms. So you know that the resistors themselves, each individually will have a mean resistance of about 100 ohms, right? If you look at the probability distribution of the resistance for each resistor. But now if I take a random sample of 25 of those, right? Think of the random sample as an experiment. If I repeat my experiment 25 times, and each experiment consists of manufacturing the resistor and measuring its resistance, then what's the probability that the average value, right, of the resistance for this sample of 25 is going to be less than 95 ohms? So let's see how we can relate this to what we just introduced. First off, you have 25 resistors. Each of those 25 resistors, right, will have a resistance, and we can say that the resistance of each of them is a random variable with a normal distribution. So I have, let's say, my resistance for my first resistor, and instead of writing it down a table, I can just plot a graph. It's going to be a normal distribution with a mean of 100 and a standard deviation of 10. All right? Now, I can grab another resistor. My second resistor will have the same normal distribution with the same mean of 100 and the same standard deviation of 10. My third resistor is going to have the same normal distribution, right? The same normal distribution with the same mean of 100 and the same standard deviation of 10. And I can keep doing this all the way up to my 25th resistor. My 25th resistor is going to have a probability distribution that's normal with the same mean of 100 and the same standard deviation of 10. Now, those are the probability distributions for each individual resistor. So for the resistance of each individual resistor. But what I would like to know is, if I were to grab the average value, the average resistance of each of those 25, I want to know what is the probability that that average resistance is less than 95 ohms. So this sampling distribution, right, of my sample mean, right? My first question would be, if I were to plot the probability distribution of my sample mean, what would that look like? I think we mentioned earlier that if the variables have the same probability distribution and they're all independent, then the sample mean will follow some type of probability distribution. It would be the same in this case because they are normal. But even if these were not normal, right, the sampling distribution would still be normal. Okay, so let's keep that in mind. The sampling distribution will follow a normal curve regardless of what these ones look like. As long as they are the same with each other, as long as they all have the same probability distribution, this will be normal. Good. And what is the mean of that sampling distribution? Take the sampling distribution, right? The mean of that, remember, is going to be exactly the same as the mean of all the others. So this one would be 100, that's correct. And what about the standard deviation of that sampling distribution? And if we need a recall, right, the variance, right, sigma squared is for each individual value, right? But then for the sampling distribution, the variance will be sigma squared over n, where n is the number of outcomes. So in this case, my standard deviation, right, would be the square root of my variance. And because my variance is sigma squared over n, then all I have is, well, let's see. Sigma is 10, sigma squared will be 100, so this will be 10 divided by the square root of the number of outcomes, which is 25. I can see that most of you wrote it down in the chat, so that's good. So square root of 25 is 5, which means that the standard deviation will be 2. Or, like Michael said, the variance would be 4. Okay? So we have all of these 25 random variables, each with their own distribution, with their own mean and their own standard deviation. If we take the average sample mean of these, right, the sample mean, then we would have our own probability distribution with the mean of 100 and a standard deviation of 2. What's pretty interesting, you can see here, is that the standard deviation is actually smaller in this case, which actually makes it easier for us to analyze, right, and for us to find confidence intervals, which we'll talk about later. Now, we would like to find the probability, right, that my average resistance, so X bar, is less than 95 ohms. Okay? If we want to find that probability and we know what we're dealing with a normal distribution, we can just standardize it, right? We can standardize this by creating a standard normal random variable, which is simply equal to my variable minus the mean divided by the standard deviation. Now, of course, you want to be careful here because the standard deviation is actually going to be the square root of the variance over n, but we already calculated it, okay? So we want to find the probability that x is less than, x bar is less than 95. So the equivalent standard number, right, for this one will be 95 minus the mean divided by the standard deviation. And this gives us, right, negative 2.5. Finally, we can go to our z-score tables. And we can see that if we want the probability that x bar is less than 95, it's actually the same as trying to find the probability that z is less than negative 2.5. We can go to our z-score tables and find that value. So what's the z-score of negative 2.5? In other words, if you may need a refresher, what those z-score tables tell us is the probability, in this case, that your outcome will be here, right? Less than negative 2.5. Remember, the mean for a standard random variable is 0. So the probability just gives us the shaded area in this bell curve. And you can find that on your z-score table. So if you go to z-score table, find negative 2.5, what is that probability going to be? So I see I see two different values in the chat. I'll just have a third person to answer. And okay, it looks like there's agreement that's about 0.6%, right? 0.006210. I saw a value that's a little bit different, 0.004799. So let's just make sure we have, let's just make sure we're looking right at the correct table. I see in the chat says that was negative 2.5 and then negative 0.09. Okay. Okay. That's good. All right. So that's essentially what all this procedure is helpful for, right? Right. We are now, instead of looking at individual random variables, so individual runs of experiments, now we're looking at experiments repeated multiple times. So we're looking at the outcomes of the experiments that are repeated multiple times themselves. Okay? So that is, right, our that is the idea behind parameter estimation. Notice that it's a little bit more helpful in terms of data collection, because now we can see, right, that even though we may not understand fully how to use the probability distributions of individual runs of an experiment, if we repeat the experiment multiple times, we will end up with a normal distribution, which is something that we can actually analyze. So it's always helpful, right, to be able to find ways or find different ways to analyze our data. So let's do a different example. And instead of actually looking at multiple variables with a normal distribution, let's look at multiple values with a continuous uniform distribution. This example is also from your book. Let's see. So let's suppose that x is a random variable with a continuous uniform distribution defined by the following equation. Okay. This is not very clear to you. We can just plot it. We see that between 4 and 6, x will have a probability density function of about 0.5. And for everything else, my probability density function will be 0. That's all it is. Okay, so it's a uniform distribution. However, our domain is only between 4 and 6. X cannot be anything less than 4 or anything greater than 6. And of course, this is a continuous random variable. Knowing what you know about continuous random variables, you know that if you take the area under this curve, you should get 1. Now that's just x, and you can run x multiple times. So each time you will have exactly the same probability distribution for your random variable x. And I'll just call it x little I, right? Which means that you can run it multiple times. Okay. I guess my first questions would be, what is the mean and what is the variance of this individual run, of this individual experiment run? So let's say this is our first time we ran the experiment. We have outcome x, and the probability distribution of the outcome is this one. So what's the mean? What's the variance? Mean should be relatively simple. Remember, a continuous probability distribution will have a mean at the point where your probability density function is split in half in terms of areas. So what is that point? The mean is 5, correct. I saw a 0.5 in the chat. I think that was a typo. I hope. And what about the standard deviation? So anybody remember what the standard deviation for a continuous uniform distribution was? If you need a recap, you can actually go to your notes on continuous uniform distributions, or if you recall, I did give you a little table that I recommended that you out, and that's kind of what the table is for, right? You can go back to your table of probability distributions and go to the continuous uniform distribution and find the column for the variance. And tell me what that variance is. Right, I see in the chat that we have b minus a squared over 12, and that's correct, right? So b minus a squared over 12 is what? I don't think we need a calculator for this one, right? Correct. It's about a third. That's correct. Good. So this is the mean, or these are the mean and the variance for one individual run of the experiment. Okay? Now, what if we take this experiment and we run it 40 times so that we have our first run, our second run, our third run, all the way up to our 40th run. And we decide to obtain, right, to obtain the sample mean of all of these experimental runs. If I plot the distribution of my sample mean, what would that distribution look like? Would it be a uniform distribution from 4 to 6? It would be a normal distribution. That's correct. So my plot would actually look like this, not like this, but rather like this. Good, that's correct. What would the mean of that sample mean be? And just to distinguish these two, I'm just going to write this as mu bar, and I'm going to write my variance as S of X bar, just so that we can distinguish them between the two. So what would my mean be? It would still be 5, that's correct. And what about my variance? What would my variance be? You can either calculate it or you can tell me what you would do to calculate it. That's correct. We would have 0.33 over 40. Here, actually, I think it's better if we just use 1 over 3. So 1 over 3 over the number of runs, which is 40, right? 3 times 40 is 120, so 1 over 120. Correct. Good. So you can see that it doesn't matter if your probability distribution is uniform, right? For the sample mean, your probability distribution will be normal. Now it is, we're about 5 minutes. We have about 5 minutes left. So let's continue the rest of the material in the next class.